welcome back to Element 14 Presents. I'm Clem and this is a Raspberry Pi Compute Module 4. It runs Linux and this is an ESP32. It does not. Or does it? Myself and all the other hosts have used a lot of Raspberry Pis in our projects, but very often this is just too bulky to embed into a project. For such cases there is the Compute Module 4 and you can directly embed it into your project, like on a carrier board. I even did one for a previous project. But the realistic sad truth is that very often you don't actually need a single board computer. A little microcontroller could do your project perfectly well, even if you want to use Python code or Wi-Fi or Bluetooth. Specialized microcontrollers like the ESP32 are perfectly capable of that. So there are cases where a Raspberry Pi might be super easy to use, but it actually isn't the best solution. It's too big, it uses a lot more power than you need, and you don't even really need Linux on there. But quite often, an ESP32 is just not big enough and you want to have like an operating system where you can give it tasks and have a bit more control like you would do on a Linux system. So people are always asking, could you run Linux on an ESP32? Until very recently, you could just say no, you can't run Linux on a microcontroller. But actually, we've seen a lot of proof of concepts where people ran Linux on very, very under-specced microcontrollers. It took hours to boot, so they were basically just proofs of concept. But now there is actually a Linux port for the Xtensa variants of ESP32 cores. So ESP32s are not all created equal. Some of them have RISC-V cores, others have the Xtensa cores, some have more than one and some only have one core. So the project we're going to do requires a specific variant, the ESP32S3. There is a cross-compiled port of the current Linux kernel, yes, the current one, to this platform, made by wonderful people that put a lot of time into this, and because I will butcher their names completely, I will put their handles and their contact details on the screen so you can see that, and also of course they are linked in the show notes. So our project is now, I want to be able to flash Linux onto an ESP32S3. I want to embed that on a module that is form factor compatible and pinout compatible with the Compute Module 4. So I could use that instead of an original Compute Module, and that would take a lot less power and it would still be like a usable Linux with Wi-Fi connection stuff for all the projects where a Raspberry Pi might be overkill or a microcontroller might not just be up to the task because of the requirements of an operating system. So let's hop over to KiCad and draft our first prototype. Welcome to my computer and KiCad. As you can see, this is a pretty complicated sheet. We have our ESP32S3 module in here. We have a few other parts like the USB port, but we also have all these subsheets here. And that is because this is actually a template that I made for not carriers for compute modules, but compute modules. So you actually have all the sections broken out into different parts. So you have your sections for all the different ways to connect to your Raspberry Pi, and you can make sub-schematics on here. So here are the connectors, and all these pins are then copied over to specific subsheets, so it's easier to organize one. I call this the pseudosum template because pseudosum is the name that I gave this thing, which means sudo is the command that you take control of everything, and then sum means system on module. So we have our main MCU/system on chip on here that should run Linux in the end. We have some connections for debug and for flashing, a reset circuitry and some caps to make it run stable, some protection, the USB port, and otherwise we just have some voltage regulators. That's it. And the connectors, of course. So we put that into a PCB. It looks like this, and it needed 4 layers just because when you look in here, the section where it goes with all the GPIOs to the actual GPIOs, it gets really complicated to route. And that is not because I want it to be complicated. I'm pretty sure I could do this on 2 layers, but I actually want the pin numbers to still correspond. So if you use like GPIO 21 on your Raspberry Pi compute module, then that code would still work with GPIO 21 on the ESP on the same thing. So as many pins that I could match to each other to have the same GPIO number, I did match them up. But this has not as much I/O as the compute module, so we can't have all the pins be the same. But whenever there's a chance to have the same pin number corresponding, so it's easier to transition your projects and stuff, then I did that. Really important, we have here this little boot header. If you close that header, module goes into download mode, then you can flash stuff to it. If you remove that, it boots normally. Of course, this doesn't only run Linux. You could also like run CircuitPython on there or flash it with the Arduino IDE as usual. It's just in the form factor of a compute module. Let's get this into production at Eisler and then assemble it. Thanks to Eisler for the PCBs for this project and many other projects. They delivered really fast and now we can go to assembly. During assembly I had a bit of trouble with aligning the CM4 headers. Turns out if you look in the actual datasheet of those headers, they do not recommend putting 2 in parallel, so that usage is actually a bit off spec. And the reason is just it's really hard to perfectly align them so they fit on the board every time, at least by hand. If you get those assembled as a circuit like with Eisler, then I don't think that's an issue. But if you're doing it by hand, be aware that it's really hard to perfectly align them. A big difference between these two is that my variant has a USB-C port on there. And that is because the Compute Module 4 can't really be used without embedding it. Even to flash it, you have to put it on some sort of carrier. But this thing here has its own USB-C port. It also has a header for a USB to UART converter, so I can flash it directly on here and don't have to embed it yet. And I could also use this standalone for projects that just need the bare bones thing, like stuff that only uses Wi-Fi and doesn't really need the GPIOs, but I could always add them later on. Now that we have working hardware, I just proved that by flashing on a Blink sketch that just outputs via serial with the Arduino IDE, so I know the chip is flashable and all the electronics work as intended. Now it's about flashing Linux onto this system.
Hello, I'm James from Workbench Wednesdays, a show about the stuff found on your electronics workbench. Look for new episodes on, well, Wednesdays. You can connect with me over on the Element 14 community. I look forward to seeing you. For now, it is time to get back to watching this week's project video.
I tried to compile the Linux kernel and this port myself, but my computer every time locks up or outright shuts off during compilation. I think I have a GCC compiler dependency error, so I won't try that again because I need the PC to edit this video. But thankfully the creators of the original port have sent me a precompiled file for that, or basically a series of files that we have to flash onto the ESP32S3 to make it boot Linux. This is the next project that we're gonna tackle. Flashing Linux on this microcontroller is a multi-step process. First we have to flash a bootloader, then we have to flash a partition table, then fill out this partition with even more files, and in the end we should have a bootable system. So I want to make that easier, so I wrote a little script for that. Flashing Linux on the ESP32S3 is a bit complicated. You have to remember a lot of commands and have to keep your ESP IDF up to date. So I made a little script that makes that easier. It is basically dependent on all these files that I got from the original creators of the port to flash them onto there, and expects those files. But you can, during the script, just enter different files if they are called differently, because you can decide that while compiling. But this makes that into a much more bearable process. It still takes around 8 to 10 minutes to flash all that stuff onto the little board. Now that we have a bootable system, we connect to it via the serial terminal. Over our USB port, I have to connect to the actual running system via UART, because the console is actually put out to the UART connection. If I would compile that kernel myself, I could also change that, I think, hopefully. Let's see if the native USB will work in time. Currently USB host and stuff is not implemented, so we can change directory and stuff, but we can't actually do very much in terms of a compute module with it yet. But we can change GPIO states, for example, at the moment. Usually we stop at one iteration, prove that it works, and then we run out of time. But this time I've pumped double shifts and there's a second PCB here. That one has two USB ports, integrates the USB UART converter, and even has another microcontroller on there. What could that mean? Let's hop on over to KiCad. Ha! Once again we're in KiCad on my computer. So we still have the same template, but I've actually drawn up a new schematic. It looks kinda like the old one, but there are some changes. Especially, for example, I have changed the little header pins to a three-headed pin because I can now solder in a switch, which will make flashing and stuff a bit more comfortable. And also, if you look in the video section, we have a whole new thing on here. This is an RP2040, the chip that is on the Raspberry Pi Pico. And I've chosen that for one specific thing, the PIOs, the programmable input-output stuff. Because you can actually make this thing output DVI, which is a subset of HDMI. So I could have basically a little pseudo GPU. I haven't done anything on the code yet, but this is basically putting it out on HDMI 0, and here would be the pins for HDMI 1. Haven't connected them yet because routing would be an absolute nightmare, and I have to get this thing into production as fast as possible. So if it's in this video, you know that I did make it fast enough. So we basically have a whole second microcontroller on here that gets commands via UART and then puts it on there. And the goal is to have this accept the same commands as the Adafruit graphics library. So you could basically wrap that into the same thing, use the same library, and when you output the commands in a program that you run on Linux, it will draw graphics on screen and not just output text. Huh? Isn't it? That's an idea. I have no idea how to pull that off in code yet, but we'll see. So anyway, important, if you use a RP2040, you have to give it external flash. That is not included into the chip, so be aware that when you calculate for cost and space on the board. Speaking of space on the board, oh boy, do we have little space. It's a 4-layer board, of course, again. But yeah, the routing got pretty complicated. Still wanted to match up all the pins whenever possible. This one here is even more complicated. Oh boy, there's a lot of stuff to route here. Basically, this section here, that is all GPU stuff, and this is basically MPU or CPU stuff, like main processor and graphics processor. But I also have this super tiny IC here, which is a USB switch, and that allows me to give that native USB functionality either to that chip or to that chip, which means that it can effectively switch places. So if you use that thing standalone or embedded into something, you don't have to run Linux. You can also run CircuitPython and Arduino or whatever, and you can use DSP as the main controller and use the other one, the RP2040, as auxiliary stuff. Or you can change it around, use the RP2040 as your main controller and use that as your Wi-Fi bridge or your Bluetooth thing. However you like, and you can use it standalone or embedded or on Linux if you want. So let's get this into production ASAP with fast shipping and stuff to Isla. So it makes it still into this video, and I have an easier time flashing stuff on here because now the UART to USB converter is integrated into the board. The assembly went okayish. I had a lot of cleanup to do. There were a lot of bridges and stuff. Really tiny components. Also, there are some experimental features like this switch that switches between the two microcontrollers to be able to program them. And as you see, I have removed the RP2040 because it shorted the system, which led to a brownout on here. It was not so easy to detect, but my finger sensed heat. And usually a chip that gets very hot but doesn't do anything usually means it's broken. So I removed it and now this thing boots and we can demo it. After booting into Linux, which actually takes about 15 seconds, we can now change folders, change directories, look at all the stuff that is there. We can see a lot of the usual Linux operating system functions are present. We can change into the /etc directory, which is the only one that we can actually write to. All the other stuff is read-only. And in this directory, we find a config file for the Wi-Fi settings. If we use VI, the built-in text editor, we can change those settings to our credentials for the local Wi-Fi, reboot the system, log in again, and then we have actual internet connection and we can ping a server. If we can ping a server, we should also be able to use wget to get files. And for that purpose, on sudosom.com, I've made an FTP server that now holds test files, which are basically just text files that I can download onto this thing, and with cat I can read that and be sure that the download happened correctly, and I can basically get files onto the system. Currently, that's the only way, because the USB host functionality is not active, so I can't put a USB stick on there or somewhere. So that is the way I currently get files onto that, or I type them in. Something really cool is also that I don't have to connect via the serial terminal if I don't want to. I can also connect via SSH. And that even works at the same time. So I'm now connected both ways. Once via USB with the serial terminal and once via SSH over a normal terminal. This is really cool. I can even do stuff on both ends. So it's actually two users on one computer, like with the old mainframes, but it's actually just a single ESP32. Crazy. Obviously, this version has a lot of things to be desired and left to do, especially for the HDMI output, and there's a lot of software that we have to do for that. There's a dedicated repo for all the software stuff called the ESP32 Playground that is linked in the show notes. There's also a dedicated repo and all the files on the Element 14 community for this handy little board and its development. There is a repo for SudoFlash, the tool to get it on there. So we've done already a lot of stuff to turn this into a thing that might go out there and could be built into a lot of projects. But I want to hear from you, your ideas on what needs to be added to this board, what kind of software support does it take to make this into a viable alternative? What are the projects that you would do that are not just not microcontroller territory, just not single board computer? There might be something in between, or just this little project where it would be just overkill to use a Raspberry Pi, but you still want to have something like an operating system. Let me know. I gotta go. There's another project waiting for me, and I'm pretty sure it involves this thing in one way or another.